This is a short video about 3.2.2 in Stein's number theory book. We'll go over a realistic Diffie-Hellman example, along with this kind of nice auxiliary result about what's an easy case to find a primitive root mod some p, some specific primes p. And so in particular, just to remind you of some of the terminology that we're going to need going forward that we've talked about in some previous videos, but maybe it's good to bring them all back up to speed. Remember that z mod p z star, those are the units mod p. So the units mod p. And what would those numbers be? Those would be the numbers 1, 2, all the way up to p minus 1. And so in particular, the order of the group is also p minus 1. But remember, a way to compute that, the order of z mod and z star in general should just be 5n, which again measures or counts how many numbers are relatively prime to your input up to that input. So in the case of a prime, all the numbers 1 through p minus 1 are relatively prime to it. So hopefully you remember that connection. So that's the order of the group, which again is what you might call the cardinality of the group in some contexts. Then we had the concept of the order of an element. And so remember, the order of an element was what's the smallest natural number m, so that g to the m is equivalent to 1 or equal to 1, depending on how you're writing things. And remember, I want the smallest such exponent that'll work. That's a natural number. And finally, if your smallest exponent happens to just be the order of the whole group, then that meant that that particular element g is a primitive root, is what we called that, or a primitive element, whatever you want to say. So in our case, when p is a prime, if you have an element g whose order is p minus 1, that g is a primitive element. I think that kind of gets up to speed with what some of the other videos have said so far. Now what we'll look at is what's a way to find a primitive element in some contexts for some primes p. For some primes p, finding a primitive element is easier than other times. And there was an algorithm back in the primitive root section, although I think I skipped it in the videos because it's not of much importance for what we're going to do going forward. But in this particular case in proposition 3.2.4, if you have a prime such that p minus 1 over 2 is also a prime, then it's actually kind of nice and easy to find a primitive element. In other words, a generator for this group, z mod p z star. To give you an example here though, p is a prime such that p minus 1 over 2 is also prime. I think something like 7 would work. 7 is prime, and 7 minus 1 over 2 would be 6 over 2, which is 3, is also prime. But if you took something like, say, 13, 13 is prime, but 13 minus 1 over 2 is 6 is not prime. So this proposition applies to numbers like 7 and 23. But this proposition 3.2.4 does not apply to some primes like 13. So just be careful again. 3.24 does not cover all the cases. It's just going to work for some primes. But if I'm in this context now, p is a prime such that p minus 1 over 2 is also prime, then what can I say about the elements, the order of the elements in this group? In other words, what's the smallest exponent that I need to raise an element to in order to get back to 1? And what you should remember too from a previous homework assignment is that the order of an element, maybe this would be good to write down too, the order of an element has to divide the order of the group. If you've had like modern algebra or abstract algebra, that's a consequence of what was called Lagrange's theorem. And we just used it for our class with Euler's theorem and with Fermat's little theorem. So in particular then, if I've got z mod p z star, its order is p minus 1, then I can tell you also that each of its elements has to have order 1, 2, p minus 1 over 2, or just p minus 1. So there are only 4 possibilities for what the order of an element in this particular group is. And again, that's when p is a prime such that half of p minus 1 is also prime. So let's take a look at the proof of this because it's kind of nice. So what we talked about earlier, since p is prime, I know that the order of this group should just be 5p, which is equal to p minus 1. Now by hypothesis, what do I know? I know that p minus 1 over 2 is a prime by hypothesis. So if you think about p minus 1 is a number, and it's not prime, I could factor it. And how can I factor it? This is kind of cool. Well, it's going to be 2, that's prime, times p minus 1 over 2. So p minus 1, in this case, has this very nice prime factorization. If you think about when you multiply that, hey, I get p minus 1 back. So p minus 1 factors into these two prime factors. So that's, in particular then, what can I say about it? So I guess where am I at? Why did I say in particular? I'm not sure. I'm here. P minus 1 has a prime factorization of 2 times P minus 1 all over 2. Now let's take any element in Z mod P Z star. And what I want to show you is that the order of A has to be one of these in this list that I've highlighted. 1, 2, P minus 1 over 2, or P minus 1. Well, what do we know from theorem 2.20? This is Euler's theorem again. And Euler's theorem, in general, reminds us or tells us that A to the phi of n should be equivalent to 1 mod n. And in the particular case that n's a prime, remember what we just said is, well, when n's prime, that's P minus 1. That should be equivalent to 1 mod P. And so that's all we're saying right here. I know that when I raise A to the P minus 1 power, I get 1. That doesn't say that P minus 1 is the order of A. It's possible that a smaller number than P minus 1 would work. And remember, the order is defined to be the smallest exponent that works. So far, the order of the group will always take you back to 1 as an exponent. If you use the order of the group as an exponent, you will always get back to 1. But that doesn't say that that's the order of the element. There could be a smaller number. But what do I know? The order of this element A, it has to divide this exponent, P minus 1. And what are the divisors of P minus 1 now? Well, according to this, 2 is a divisor, P minus 1 over 2 is a divisor, and of course 1 and P minus 1 itself are the only other two divisors. And that completes the proof. So there's only 4 possibilities for what the order of A could be, since it has to divide P minus 1 by Euler's theorem. To give you maybe a concrete example down here about why is this useful to find a primitive element, in other words, what's a generator for a particular group, let's play around with the case that P is 23, because then P minus 1 over 2 would be 22 over 2, which is 11, which is prime. So the theorem, or the proposition, applies to this number P. So what do I want to do? Let's look at the number 2. And, well, one possibility is that 2 already has order P minus 1. So if 2 has order P minus 1, we're done. And what do I mean we're done? The goal here is to find an element of order P minus 1. Well, it could just be 2 right off the bat. So in our case, it is possible. But what we need to make sure is, does a smaller exponent work? And so the other possibilities for exponents on 2 would be, we need to check exponents of 1, 2, and P minus 1 over 2. So P minus 1 is guaranteed to work. In other words, 2 raised to the 22nd is guaranteed to get me back to 1 mod 23. But what I'm saying is, how do I know one of these guys doesn't do the job before 22 does? So what you would do is you check. Well, 2 to the 1 is definitely not 1 mod 23. And 2 to the 2nd is 4, which is not 1 mod 23. So the last one we need to check is P minus 1 over 2 here. And so in that case, P minus 1 over 2, which is of 11, right? And so 2 to the 11th mod 23, that does happen to be congruent to 1. So far, where am I at? In my example here, 2 has order 11. So it has order P minus 1 over 2. How do I find an element that has order P minus 1? Remember, that's the goal. It happens to be minus 2. So once you see that 2 is an element of order P minus 1 over 2, then your primitive element could just be negative 2. And so negative 2, when you're thinking about that, when P is 23, negative 2 would be what, 21? Anyway, though, why is negative 2? Just as the author says here, I'm trying to give you a concrete example about this part right here. Then negative 2 has order P minus 1, just to show you why this works. Negative 2 raised to the P minus 1 over 2, that's really the only other possibility for what the order might be. It's obviously not 1, it's obviously not 2. How do I know it's not this next smallest one? Well, that's because that would be minus 1 to the P minus 1 over 2 times 2 to the P minus 1 over 2. Just using exponent rules, we still get those. Well, this is minus 1 to the 11th, though, and that's an odd power, which means the minus sign's sticking around. That's still minus 1. And then 2 to the P minus 1 over 2, that's 2 to the 11th, which we just computed was 1. So what am I trying to say here? Negative 2 to the 11th is not 1, it's negative 1. So what did that just justify? Mod 23. What I'm trying to justify is that 11 won't cut it as an exponent on negative 2 either. Therefore, we have to use our biggest exponent, our biggest possibility, which of course is just P minus 1 itself. And so negative 2 has order 22. And again, that would be a primitive element for that group. In other words, you could achieve all the elements of Z mod 23 star by just taking powers of 2. The powers of 2 should cycle through all the elements of Z mod 23Z star. Down below here is kind of an example with some big numbers, a big N and a big M for the Diffie-Hellman exchange. It's very similar to what we looked at in the previous video when we introduced the idea of why don't I put the secret key, N and M, why don't I use those as exponents instead of just products or factors. And for these, this book's a little bit, we did find a typo here. Let's see, the Q, we're gonna look at this number Q here. And so that means that going forward, these should all be Q's instead of P's, I believe. And so what we'll look at though is there's my Q. Q's the prime that Michael and Nikita agree on. And then now Nikita's secretly gonna pick this N, so only she knows it. And Michael secretly picks this M, so only he knows it. And he does not share that with her, and she does not share her N with him. What they do share with each other is G, and where is G? What G did we pick here? Did they pick a G yet? -2, so -2 will work as a G, I think is what they're using. And so they're going to take -2 raised to Nikita's power is that. So that is what she sends kind of over the airwaves that anybody could see. And Michael is going to send -2 to his M power, and he sends that back to her over the airwaves. And again, the idea here is that theoretically, only they could compute G to the N times M power, and that's their secret key. That's the secret that, again, only the two of them know. And that's how they would use that later on, you'll see, to like decrypt messages. And this is just kind of an example about how they are implementing some of this in Sage, just to show you how some of these numbers work. So this dot is prime checks, is this number Q a prime once you've defined it? And then the next one we want to check is it true that Q minus 1 over 2 is prime? In which case, by the above, if I wanted a good primitive element, I'll just let G be -2 mod Q. And what they do is they check it. When you check the order of G mod Q, you get this number here that ends in 22. And notice it's just one less than the Q that ends in 23. So Q, this one, and this one, this is P minus 1 according to my examples above, how I denoted them. And so after that though, we just had Sage compute some things here, and at the end, just to also make sure, when Nikita sends this over the airwaves, that's going to mean something. We'll give some context to it soon. Michael sends this back over the airwaves, and the idea though is they could both use their N and their M in order to achieve the same secret key that only they would know. Now, the Diffie-Hellman key exchange is susceptible to what's called the man-in-the-middle attack. I'll try to draw you a picture about that in a moment, but so far I like how the setting goes here. So instead of talking on the phone, they're going to communicate by like text messages, say. But the eavesdropper, which we'll call the man, they're going to watch each of the transmissions, and he can intercept messages and he can send false messages. And so how is he going to do that? And so if I was going to give you maybe a picture over on the side, which I'll try to do, I've got, say, Nikita, and I'll draw a little bubble for her. And I've got Michael, and I'll draw a little bubble for him. And they've got some secret information, say. So let me kind of make up some numbers here. So let's say the secret N, hers was 31 in the examples we've been doing. And we've had some public information, right? Like, so public I'll put out here. P was 97 for their examples. And what else? Was there another one? Oh, G was equal to 5 in the examples we were doing earlier. Michael's secret earlier was 95. So just trying to be consistent with what the book has already done. And now what we're saying is, normally she would just send, 5 to the 31st to Michael, what the value of that is. Except, of course, they don't know, like no one sees the 31. She just sends the output of that. So G to the N, she just sends, in our case, what is G to the N mod P? I don't remember now. It's 7, I think. And then he sends back to her G to the M mod P, which is equal to, I think earlier it should be 39. And then they would both have a secret key that only they know, where the secret, S, was 14. So I'm trying to draw this where if it's in the bubble, then that's information that only they know. But if it's outside their bubbles, then that's public information. But now the idea is, what's this man-in-the-middle attack? Well, when they send this to each other, there's somebody that is literally kind of in the middle. And since I didn't leave myself a lot of room, I'll put him down here. So here's the man. And here's what the man's going to do. Instead of Nikita just sending G to the N over to Michael, he's going to intercept that first. So he's going to intercept that message. Here's what G to the N is. And he's going to make up his own number. He's going to make up his own number, say T, and let's say T is 29. And what he's going to do is he's going to send Michael G to the T. Then what's going to happen? Michael thinks he's going to send G to the M back this way, thinking it's going to Nikita, but it's actually going to the man. So that now the man and Michael have a secret key. Michael thinks that he's talking to Nikita, but the whole time he's actually talking to the man. So now Michael and the man have a shared secret key that use the exponents T and M. Similarly, Nikita thinks she's talking to Michael the whole time, but actually the man's going to send her back G to the T as well. And so now they have their own secret key. And so the man has literally placed himself in the middle to intercept these messages. Now he shares a secret key with each one of them, and he can impersonate each one in order to, say, steal information, just like it says. And so their secret key would be, for Nikita and for the man, it would be G to the T times N. That would be the product of their exponents there. And the secret key for Michael and the man would be G to the T times M. So then the man has secret keys with each one of them, which allows him to impersonate each person. That's bad. Man in the middle, not good. It's a big drawback of the Diffie-Hellman key exchange. And there are ways to get around that, like digital signatures, but we won't get into digital signatures in this class. But what we will look at is RSA, which is a little bit stronger.